Hello students and welcome to another video. I'm your teacher Mr. Flynn, and today we're going to be talking about intermolecular forces. Alright, now what does intermolecular mean? Well, I'll just go with the title here. So inter, means between molecules. Alright, so before in chapter 3 we talked about intramolecular compounds. So for example, if we have H2O, what we're looking at is an oxygen bonding with hydrogens like this. Now, these bonds are intramolecular forces. They're happening within the molecule itself. Now, what happens when you have an oxygen, another hydrogen, another water molecule, interacting with another water molecule? Well, we call that now an intermolecular force. All right, we call that an intermolecular force. All right, and it's the type of interactions that are happening between molecules. So we're kind of working our way out again, and that's actually what this little icon is showing you. It's showing you these, in my mind, these are ammonia molecules, and they're interacting. And this little black line here is that intermolecular force that's attracting them together. Okay? All right, so let me clear this out, and then we'll head down below and look at our notes. All right. So we're going to be on this left side here, and we're going to work our way down, okay? Now, there's three types. We have dispersion forces, dipole interactions, and hydrogen bonding. So these are our three main types. And they kind of go in order of strength. So dispersion is the weakest, and the strongest is hydrogen bonding. Oh my gosh, I am just killing it here. Not hydrogen, it is the strongest. I said the word that I was writing. All right, so this is the strongest, and this one's the weakest up here. So let's start with the weakest, okay? Now, dispersion forces are temporary. They are not permanent. They come and go. And let me explain how that works. Neon is an example we've been using in several of our videos. And neon doesn't like to interact with anything because it has a full octet. It has a full shell. It has all 8 electrons. So if I draw my electrons on here, it's got 8, and it's happily existing. But every now and again, these electrons over here shift around, and these electrons here shift around. And as these electrons move around our atom, it creates a temporary dipole. It creates a positive end and a negative end. And what it does is when these positive and negative ends come together, they actually are attracted just ever slightly. Okay, and we call these dispersion forces because those electrons are being dispersed, and as they move around, they every now and again are attracted to each other just because of where the electrons are. Okay. Now, in some instances, the electrons can actually be pulled around and pushed around, and they create these little temporary dipoles, and when you pull them away from each other, they go right back to being neutral. Okay. So these dispersion forces are also called London dispersion forces, so you may hear that term every now and again, London dispersion forces. All right. But this one is temporary, and it is the weakest, and it only exists for a moment. Okay. So when they move around, all right, that they'll have like a slight connection. All right, the next one are dipole interactions, and these are permanent. Okay. The dipole that exists, a dipole is this right here. It's this black arrow. It points from the positive end to the negative end. And just to clarify, a lot of you are probably thinking, Mr. Flynn, I don't know what this is, this little plus thing. It looks like this. All right, it means a partial charge. It's not a full charge, it is a partial charge. So this is a partially positive end, and this is the partially negative end. And it's pointing to where the electrons are being shared or hogged. So in this example, we have chlorine and iodine combined. And we're going to have the iodine and chlorine, they are both takers. They're both nonmetals. All right, so these are going to share, or they're not going to share evenly, okay? This iodine does not like to hold on to its electron as much as chlorine does. So chlorine's going to hog that electron a little bit. It's going to have a negative side, and iodine's going to have a positive side. Okay, and as I go through this, it creates this bond, and we call this the dipole interaction. Now it says bond, but really what it is a interaction. That's the word I'd rather use. But if you're going to see it in textbooks, you're going to see it in other places, they'll say it's a bond because the partially negative and partially positive ends are going to be attracted to each other. All right. And so it is bonding, but when we're talking about intermolecular forces going between molecules, because this is a molecule, this is a molecule, we're going to talk about that as like an interaction, all right, to kind of separate and kind of make it more black and white for you, okay? All right, and it's all directed by a dipole, which is our positive and our negative end, okay? And it acts like a small magnet, okay? There's a positive and negative end. And we've talked about this with water. Now, water is a special type of dipole interaction, okay? And that is it has very strong dipole interactions. So we have our partially positive and negative ends of our water molecule, and the negative end is going to be combining and matching up with a hydrogen on the other water molecule, so we just call it a hydrogen bond or hydrogen interaction. Okay, now not all elements that contain hydrogen are going to make hydrogen bonds. For example, this methane molecule, okay, it's actually neutral. This carbon is equally sharing the charges around the molecule, and this can be quite challenging because you have to think about molecules in a three-dimensional shape. Like this forms a tetrahedral shape, and the charges are being evenly distributed. There's not a dipole found in this methane, so it's not going to have a hydrogen bond. Okay, so just pay attention to what atoms or what molecules you're working with, because some molecules won't have dipoles in them, and they aren't going to hydrogen bond. So just pay attention to this. That's why I put this in here, okay? So the water molecules, they're going to hydrogen bond, and that's going to be the example we use like all year. Is when we talk about hydrogen bonding, it's most likely going to be water molecules. But there are others, okay, like ammonia hydrogen bonds, but it also has variations in degrees to how strong those bonds are. If you want to see a good example, turn to page, I believe it's 151 in the textbook, and you can find a nice picture of two different types of hydrogen bonding and how the strength of that bond is influenced by the electronegativity difference, okay, between ammonia and oxygen and hydrogen. So just, if you want a nice example, you can look at that, and that's also going to be part of your proof, I believe, as well. Okay? All right, now, that's as far as I want to go, but I'll talk about liquid versus frozen water. This is just a review from last year. I'll talk about this in this video. We have these, you know what, actually, I will talk about it in the next video. We'll talk about it in the next video because it's going to be talking about water, and I'll just review it then. Up here, we have dispersion forces, dipole interactions, and hydrogen bonding. These are our three main types of interactions, okay? And the dipoles are determining, okay, for the hydrogen bonding and dipole interactions, the bond or interaction that's occurring there.